Thanks a lot for coming. We are going to have a session about that's not me.
You're number 4, that's you.
About a reactive game stack that is using Erlang, Lua and Voltdb. So what we're going to look at is what is the reactive paradigm. There's a reactive manifesto out there that is having quite some feedback. Then we're looking at specific challenges that a game server has, but that are general to lots of types of servers. We have the ambitious goal of getting a game server stack together that can break the EVE record and have 10K ships in one sector. But that's not quite as far as we're going tonight. And at one point, when this PowerPoint is uploaded, you will see the sources on GitHub that we haven't had the time to make pretty yet. So if somebody's interested, can look at more stuff and go deeper into it there.
Yeah, hi. Okay, so I'm Robert Virding. I am one of the original people who developed Erlang way back at Ericsson, and I now work for Erlang Solutions. So I'm a very old Erlang person.
Yeah, I'm Henning Diedrich, and one part of the tech that we're using here is the bridge between Erlang and Voltdb, and that's what I've contributed. So now this should work. Let's see. Now we can flip. Now we're going to show you a fierce battle.
Yeah.
So that's our universe.
We do that and we start things up. What happened now? Oh, of course I misspelled it. Sorry. So yeah. So what we're seeing here are ships moving around. If you see the red ships, they're attacking ships. So every time they get close to one of the white ships, they zap it. Right. And those funny little square things, they are explosions. I'm not a graphics person. Okay. So we'd start up in that space with 1,000 ships running at the beginning. It was completely parallel, each ship, and everything was completely asynchronous to communication between the ships. So when one ship saps another, it's completely asynchronous communication between it. And the Erlang system, as I'll show later, provides automatic scheduling over the cores and load balancing over the cores we have in our machine.
So what we've put together here is a nested stack that has Lua running in Erlang. And that's a pet project that Robert has started, where he has implemented a Lua interpreter in Erlang. And that is coupled with a high-velocity database where the state of the individual ships is written back into, and that's Voltdb.
Yeah. So the whole system is event-driven. So there are messages being passed between the actual ships, between the system to the ship, for example, between the ships and so on. It's completely scalable in the sense that we'll use the resources the machine gives. So, okay, now it's resilient in the fact that it can handle errors. So if you get an error in the code of one of the ships, all that will happen is that ship will actually just die, but the rest of the system will keep on going. And it's responsive. It's a soft real-time system. So nothing you can do in any of the ships in your code will ever block the system as a whole.
I have a question. I mean, who here has worked with Erlang before? And who here has worked with Lua before? Oh, interesting. Yeah. Who has worked with asynchronous systems? Okay. Interesting. Okay. So then I'm going to make it fast. The general problem, or the general point why you want to have asynchronous stuff is, of course, that you have the problem that when you have a synchronous call and an answer, then you have a wait time. And if you have a overlapping call, then you are pretty fast in a deadlock. The same goes for shared memory. When you have shared memory, that's a good thing because that's a good way to interface between processes. But on the other hand, usually the point is that you read and then write to your memory, and then if somebody else writes to the same memory, one of you loses what he has written. When two processes read and then write to the same memory, it's the same. One of them will lose the changes that he wrote to the memory. And that's why usually you will have locks. And make a lock, then read, then write. But again, if you try to make a lock from another process in a way that if you have two different memory sections that you want to access, you are pretty fast in a deadlock. And this is why, to avoid deadlocks, just Erlang was developed from the ground up to have no shared memory between processes. That's why they call processes and not threads. And why you have asynchronous messages as means to communicate between processes. And that's deep ingrained in Erlang. And by the way that Lua is implemented on top of Erlang, Lua basically inherits that.
So yeah, the Erlang scheduling, so the processes we're talking about here, the Erlang processes, they aren't operating system processes. The operating system processes are way too heavy for the type of things we're interested in. So the Erlang has implements its own processor and has its own scheduling mechanism to do that. Erlang processors are very light. Here we're running just 1,000 ships. It's more, the goal, the limit here is more than how much you can actually see on the display, whether it's 10,000 or 100,000, as we could easily do. The Erlang scheduler system, or their scheduling system inside, guarantees that you will never block the system. Nothing you can do in a process will block it. There's a preemptive scheduler which makes sure that everything comes in. So one of the goals behind the language which we're using here is the fact that it is very low latency for things.
Of course, then you can still shoot yourself in the foot, even if you have all the goodness of Erlang and that it doesn't break itself. When you do something then from the language itself, where you go into a blocking function where you send a message and then wait blocking for the answer, and you do that on two sides, you have the same effect again. So you have to watch out, even if the Erlang scheduler does a lot for your security, you would still have to learn to program in a way that you use asynchronicity in the way that you are sending something and then don't wait blocking for it. And that is a quite different way of going about designing a system. So what's the basic idea of the simulation that we just saw? Each of these ships is one of these processes that is scheduled by the scheduler. The scheduler, as Robert just said, is in effect, there's one scheduler per system thread. One of those schedulers then has 100 ships, 100 microprocessors, so to say, that are all completely separate from each other. They are not sharing any memory, and they also do not, by default, have functions that they're calling against each other, but they're just sending each other messages, and by default are not waiting for an answer. So they communicate completely as asynchronicity, and the ship logic that is programmed in Lua can therefore be replaced in runtime. That's something we're going to show you in a bit. At the same time, there's a continuous write to the database, which is also completely asynchronous. There's no wait time. It's not that you wait for an answer back from the database, but the nature of Voltdb is that you just write and then forget about it. So for the demo screen that we've shown here, we're using ESDL2, which is a pretty cool new pet project from Loic, who is bringing SDL2 to Erlang.
Okay, yeah. So the ships are, well, they are Erlang processors, which are very close to being actors, and everything is asynchronous between them. As Henning's mentioned, the basic communication protocol in Erlang is asynchronous message passing. And really, it's the only protocol for. So everything is asynchronous. And the writes to the database, they're also asynchronous. So when the ships are communicating between each other, which for example, they're doing when they're zapping each other, they never wait for the result. And when they're writing out to the database, it's sent off, and there's no pause in the ship execution to do that.
The sample machine that we're using here, just for curiosity, is a 4-dual-core CPU, and we're using the newest Erlang, a certain Lua version that Lua is written for. And now time for the next demo.
If we flip over, does it work? Yes. Wait, it comes back up again. Yes. Okay, now we can see there aren't many ships left. So the whole time this thing's been going on, the battle's been continuing and they've been killing ships. There are not very many die very quickly at the moment because there aren't so many left, but they're moving around. What I want to try and demonstrate now is how you can change how code can be modified while the system is running on each ship. So we'll just writing a system to set up the 5,000 ships. We've actually created already the ships now, so we're just going to start the run, and we're doing it. This is the tick time, 50 milliseconds. So now we're running. So now the ships again are running. And with for these simple ships, the same ones we saw before, they're just randomly moving around. They'll just start off in a direction. They'll keep going to the direction until they get to the edge of the screen, the edge of the universe, in which case they'll just bounce back again. So yeah, it's a very simple one, but that just keeps on going the whole time. So what we can do now is we can change the code of the ships. So we can change to another ship code we call run ship, and we'll start off by just changing we'll start off by doing changing half of the ships first.
That's 10 too much.
That's 10 too much. A bit over enthusiastic, sorry. So now we've changed the code of 500 ships. And if you start looking there, you'll see some of the ships have become red and some have become green. Now the green ships, if we follow here, you'll start seeing they're moving out towards the edge and when they get to the edge, they're going round. They're going round and round and round. So we've actually updated the code in those ships. So now we have, so they're flying. When they get to the edge, they'll steer. So now we've got two types of ships here. One running the original code, and the other running the newer modified code. And they're actually running different code. It's not that all the ships have the same code and we're flipping a switch. We've actually modified the code of the ships. And we can do that by now doing that with the rest of the ships as well. So now we will go from 501 up to 1,000. And if we start looking now, we'll see now all the ships are running the new code. So now they're all none of the ships running the old code. We can go back to the old code if we wanted to. There's nothing stopping us doing that. But we are actually modifying the code of the ship. So each ship has its own set of code it's running. Yeah. And we could also let's have some fun. Well, we'll have some fun. Sorry, I can't help myself here. Let's start killing some things. So we'll start running a few attack ships on this system now. We'll run 100 of them. We'll be very destructive here. So now we're setting the first 100 ships to become attack ships. And now they're moving around and killing things in the system here. You can see the explosions. And when they get out to the edge of the universe where there's a lot of ships, things are dying very quickly. You can also see the system beside is actually writing out information every time a ship dies. And we're not just killing the Lua ship, we're actually killing the Erlang processors at the same time we're doing this. So now we've had ships running, 3 different types of ships running code here, and we've been able to modify the code while the system is running on the ships.
And then the nice thing, for everybody who did Lua is it's really every dot is an individual Lua state. It has its complete and individual variable state. It has its code, which we can even switch. And And when they disappear, they really kind of disappear. That's what Erlang is doing. The processes are culled, and then that state doesn't exist anymore. And that happens in a pretty decent speed. It happens with really high robustness. Even while we were experimenting and producing deadlocks, where ships were blocked and then all of a sudden were gone, due to the nature of Erlang, you don't have to worry. It's not pulling down your system if you have some deadlocks in some code. Some of your Lua scripts might be faulty. It doesn't matter.
Yeah, it was quite fun to see because you see some of the ships just standing there being blocked while the rest were keeping on going.
Yeah.
So when we're starting, this just a quick description of the start of the system. We start up the Erlang system, which I showed you was doing, and then when I was doing the start command, that initiated everything. It created the universe, it created the graphics. It actually started up the number of ships I said when I was doing that. Then when it did the start run, that actually gets all the ships moving. That just starts the motion of each ship. And the argument I gave there was the tick for the moving step. So I was giving 50, so it was a 50 millisecond tick for the ship movements. That actually can change that while the system is running. Again, if you feel like you want to do this. So the whole system, in that sense, is very dynamic. And the ticks, so what happens is that every time a ship gets a tick, it calls a tick function. We'll show an example of that in a moment, which is written in Lua and does all the logic for how the ship is going to move. And it will set a few parameters saying how the ship is going to move. If the ship is moving around in sectors in space, it can go out and ask the universe which ships are in this sector, and it will get back a list of ships from the sector. And it could decide, well, we don't have code for it now, but we could decide to follow a ship, or we could decide to zap a ship, which is what we're doing in the first case when you're doing the explosions for it. Yeah,
as we explained, there's one script per ship in the extreme. Each state in itself, like in the sense of the Lua state, as you know it from when you embed Lua in C, or use it from the C side, is in Erlang immutable, which is pretty interesting because that means you can replicate them pretty fast. And the scripts are interpreted by a Erlang program in the end. So this is an example. This is simply the movement of the individual dots in the simplest example that we showed in the beginning. It's pretty obvious. We're just adding a bit to X and a bit to Y. Then we're checking whether we're out of bound. And when we're not, then we return the new, in the end, we return the new coordinates. This is the main tick function, which is actually called every tick, every frame. So there we're doing at the first line exactly what we just had looked at. We are moving and possibly bouncing. Then we're looking at sectors. That is, in the moment, how we are checking whether there's somebody close that could be zapped. And what we're doing there is that we're looking up what sector have we been in, then we're deciding what sector are we going to now. And then when that sector is a different sector, we're looking whether there are ships nearby in that new sector. And when they are, then we are zapping them, at least the first one. And at the bottom, you see the call where the ship is actually set to the screen, which in our case is only happening in the moment that the sector is changed, which is fine for us. It gives a good enough animation. And after that, you see the update function where we are writing some stats into the database. This is the function how we zap the ship. Pretty easy. And the interesting thing is that this really kills the process.
Okay, yeah. So we're using here, we're using it while we're developing the system, the resilience of the Erlang system, or the Erlang language, in that if a process crashes, or when a process crashes, it will not crash anything else. It will not take down the Erlang system. Only that Erlang process will crash, which means it's relatively simple compared to most other systems to build truly fault-tolerant systems. I mean, if I was running something like a Java system and I did a divide by zero in Java, I'd take down the whole Java thing. Or the same thing if I was running Node. In Erlang, if that was to happen, the only thing that would die would be just that Erlang process, and the rest of the processes would not be affected. The reason we call them processes are, as Henning mentioned, that they are not sharing state. They are not sharing memory between processes. So when one process crashes, it will not ruin the state of another process. You will not get the effect that something might be half written or half overwritten or something like this. That does just not occur in the system itself. This allows you to build very fault-tolerant systems. The processes are small by default, and the Lua state is actually quite small as well. I think we're up around about some 5 or 6K state for each Lua system running in each process. So it's not very big. Okay, we're not running much Lua code, but it's quite small. There's no in the system deadlocks from blocking calls. We just don't do blocking calls between the system. We don't have deadlocks from shared memory. And the Erlang systems that we'll show in a moment gives us all the benefits of running multi-core on the system, of truly using the parallelism in the actual system for free. And yeah, well, the responsiveness is guaranteed by the Erlang VM. So as I mentioned before, there are preemptive schedulers in the Erlang virtual machine, which guarantee that no Erlang process will ever block the system. Even if you write something that goes into a tight loop, it will not block the system. It will be scheduled out, which means that you guarantee responsiveness and low latency for the system for it. And yeah, we're using messages to send between processes. So some of the calls here look like Lua calls, but underneath they're actually sending messages in between the processes. So for example, the universe is a process containing the universe, and when you ask questions to it, you send messages to the universe, which then sends back a reply message for it. And the same thing with the graphics system as well.
So looking at the tools that we've been using, Erlang stands out for asynchronicity. It's robust, as Robert just said. It's battle tested for 20 years, even if it's still gaining in popularity. And it's very productive. There have been studies, even by Motorola, that said Erlang code is up to 4 times shorter than comparable code written for the same thing. Then we have Lua. That is a staple in gaming. I mean, many games are scripted in Lua. It has a very clear and simple syntax, almost pseudocode-like. And we have the special Lua here, that is Lua in microprocessors. Then we have Voltdb. That is an asynchronous database. It's very, very fast. It can write millions of updates per second. It has near real-time statistics abilities in its materialized views. And it's very safe because there's replication built in, even across data centers if you need that in the professional license. This is how the database looks. Voltdb is a SQL database. It's swimming in the pond, certainly, of the NoSQLs. But in the end, what you're looking at here is a very familiar table definition. And you have some special code in the end that's partition table on column ID, which tells Voltdb how to distribute the data that it's going to get when it's running in a cluster. This is how an update looks in Voltdb. There's a price to pay for the speed, and that is that stored procedures in Voltdb are essentially written in Java. The reason is that they are compiled into the server when the catalog is built, and this is basically becoming part of the server, and this is why it's so incredibly fast. It's a very vanilla Java code here. You can see the update in the middle. That's completely normal SQL. And you can see the variables that we saw on the other hand, in the Lua code that we had sent towards the database. This is interesting and special about Voltdb, where you tell it how to deploy when it's a cluster, and the moment we're running it on the laptop. But usually you would make tests in a cluster that I've done in the cloud, where you could have many nodes, and this is where you tell it how many nodes it has and whether you are using replication. That's the K factor. In the moment here, it's off. Yeah, but that's basically it. That's basically what you have to tell it on top of what you would have to tell MySQL, where all that does not exist. And then all the rest you get transparent. It's distributed across clusters. There's this incredible high speed, even, and with a big cluster, you can have millions of operations per second. And this is a materialized view that's also completely vanilla SQL, where you can have a high score, and who does gaming knows that high scores are pretty tricky. So Voltdb can put you ahead here when it's simply with one materialized view keeping track of what the high score is for a ship. Now Voltdb is called in our cluster called in our stack from Erlang. And as I said, that's the driver I have written to make the connection between Erlang and Voltdb. And this is how it looks when you make a call from Erlang to Voltdb. Again, you recognize the parameters that we had used. Move is in this case in the middle. That is the name of the stored procedure. And the rest is an Erlang call. So yeah, that's almost at the end of it already. We're going to show you a little bit more destruction and what the scheduler can do. We have looked at the 4 attributes that are usually used to define reactive. And yeah, over to Robert for one last destruction run.
So what I've done now is I've set up another space with just the ships moving around. We're not doing anything destructive at the moment, just running them around. And what I've done is I've started up another Erlang system running an observer on the system running the ships. So what we see here are the dynamic graphs from the load balancing system. So what is happening is that we're running 6 separate schedulers in the game engine. And we're seeing the displays of the load of each of those 6. And the Erlang system has by default spread things out. I haven't told it to run. I haven't told it how to spread things out. I've told it to use six schedulers. It's using six schedulers. It's doing the load balancing between the schedulers itself and moving things around. That's the goal of the system, to do that. And there is control of how you want to do that. If you want to spread things out, if you want to compact them, by default, it tries to spread things out as evenly as possible. You can see it's doing a pretty good job of the load here. It's not that much load on it, but anyway, yeah. We can also see how the memory is going and things like this for it, and the I/O usage, which is not great. There are alternatives. I'm not going to show them, but we can do things like, so there are 2 mechanisms in the load balancing that work. One that tries to spread the load as evenly as possible, and another one that tries to compact it and say, okay, yes, I might have said I want six schedulers here, but I'm not using them. And then it will try and cut them down and only use as many as necessary, and it will then try and shut down cores of the process to do that. So it will actually try and save energy automatically. And this is just built into the system. So you have these 2 mechanisms working against each other, and you can control how you want them to work. Do I want to compact or don't I want to compact for it? So here we're just running it on. And we can see the system stable. The memory usage is stable and the load is stable. So what I can do now is I can start running some attack ships, which start killing things. I'm an old gamer, so I'm used to killing things in games, right? So now I've started the attack ships here, and we can see that things are dying. And if we start looking at the load, we'll see in a moment that the load is actually decreasing. As ships die at the other end, we'll see the load is decreasing. We can already see that the memory is decreasing. The memory increase was slight when I put new code into 50 of the ships. And now we see as the ships are dying, the memory usage is going down. So when an Erlang process dies, its memory is reclaimed from the system. And we can also see on the load that there's less work to do. There are less processes going on, and the load is slowly going down, slowly decreasing. We can also see that it's still trying its best to keep the load balance between the system. And this functionality is built into the Erlang system. So this tool I'm using here called Observer, that is part of the Erlang release. So now I'm running on two separate Erlangs. One Erlang which is just the game, and another Erlang which is displaying statistics from it. And there are other things I can do here as well too. I can just get more figures, for example, of what's going on, how many processes we have, how much memory is being used, etc. for them. This thing down here, this table, gives information about how the various garbage collection algorithms of parts of the memory system are working in the system. And we can see, if we look for a moment, we'll see the processes are slowly dying here. So we started off with about 1,050 processes. Now we're slowly going down as things are getting killed. And I've got the load charts here, and we see it's dropping. There's another interesting thing here. I'm using some internal Erlang data tables to keep data about the system. And here I can go look at these tables in real time, and we'll see every time the displays change, we'll see there's less data in each of the tables because each table has one record per process, and it's going down. So yeah, there's the universe which keeps track of where things are. There's the sim master which just allows me to access a game process just by its index, and the ESDL server keeps information about how it's going to display each process. It's the one that keeps track of what's in there. So we can, for example, look at the data. I'm almost done here. But this just shows for the ESDL what information's in there and how it's going to display it, what type it is. The type ship just gives information about what it's going to do about it. And the observer, the interesting thing here is that, yes, the observer is part of the Erlang release. So it's part of the standard system. But what's even more interesting, that all the tools it uses to get this information are also part of the standard Erlang system. So it's not doing anything secret or any backdoors or anything like this. The way it's using to get information is completely free, which is and gives you another feature of Erlang that makes it very easy, or comparatively easy, to monitor and look at the system while the system is running. And in production systems. So if you have a production server running, you can start looking at the server while it's running and trying to understand what's happening if something's going wrong. You can, for example, look at when messages are sent, who's sending them, etc., things like this. And here we can see, by the way, the load balance now, that the pink core, or the violet-colored core there, is deciding it doesn't really need that anymore. That and the light blue ones, they're almost not being used anymore now. And this is just built in. As it goes down, it will be using less and less of the schedulers because it doesn't need them for the load. And this is going on automatically for it.
So what we're seeing here is completely open source. And this kind of stack is something where Robert and I have basically made it possible to glue this together, because Robert has created this bridge between Erlang and Lua in this way. Certainly, it has been possible before to embed Lua into Erlang, but in a way that was kind of against the grain of Erlang, and was canceling out lots of the good stuff that we've shown here now that only works with Lua, where Lua really becomes part of Erlang, and by that super safe and super distributable. And on the other hand, I have built a bridge, let's say, between Erlang and Voltdb, and it's actually been done specifically for games, and specifically for being able to leverage the power that Voltdb has in this high throughput area, and this very quick information that comes back from the SQL database with fully ACID attributes, which is not possible when you're using NoSQLs. So this stack of Erlang, Lua, and Voltdb is something that is going to mature over time. We're still having a 0 in front of our version numbers of the individual glue parts. Still, I think it's going to open new possibilities, especially when we're using exclusively open source stuff here.
Yep.
Yeah, and that's already closing the session. Do you have any questions?
Already? Oh.
Sure.
Yep.
Yes, could you talk a little bit more about how this interfaces with SDL? I think you mentioned SDL binding.
Yes.
Is that like new? I mean, how ready is that, and how does that interface with Erlang?
Sure. The question was, how does this interface with SDL? So SDL is been used here with ESDL2, which is a project that Loic has created lately, who also brought us Cowboy, among other things. Every Erlanger knows it. And that is built directly as function calls from Erlang. You can access, you're calling, you're setting dots, you're calling render, and you have a loop in Erlang that is called every time that you render a new frame. So it's a pretty straightforward implementation where you have SDL compiled on your computer, and Erlang is tapping right into the C stuff from specifically created C library functions. Another question? Sure.
Steve, so you've defined sectors. How big are these sectors? Are they 6 or 8 pixels?
They're okay. Display-wise, they're 2 by 2 pixels. Okay, it's we're actually using sectors for two things, well, two separate things. One is keeping track of splitting the universe up into sectors, and so keep track of how you can work out ask how many ships are in one sector. And the other is for the display reason, or for doing the display. And now they're the same, but they wouldn't have to be. I mean, if you wanted to change this, you could have one universe sector displayed over a much larger thing here.
It's misleading to even talk about how big the sectors are. It doesn't matter. For us, it was easier to cheat a fast visualization of what's really going on underneath without putting too much load that's not really needed for the core of it. But the sector here, of course, does the usual service of being able to give you a means to have a visibility check without having to check the cross product of all chips in the universe. So, and for that, it works perfectly well, and it's even a very good illustration that we have so many sectors, like we have 10,000 in this case, 25,000.
Yeah, well, it's 350 by 500
whatever
at the moment, whatever that is.
Many.
Yeah.
And and that works pretty well. And it does exactly that. The zapping is doing as I showed. Whenever you change the sector, it's then doing the look around into the other sectors that are in front of it, which is pretty much what you would be doing if you would be doing a serious project. Another question? Yeah, please.
Why did you pick 6 as the number of schedulers?
Pardon?
Why did you pick 6 schedulers? You said there were 6.
So the question is, why did we pick 6 schedulers?
Okay, so this is basically a 4-core machine with dual on each. So there are basically 8 cores. If by default we use 8, I just chose to reserve 1 for the observer state and 1 for VoltDB. I could have done more or less depending on. I didn't need all the 6 for it, but yeah.
That's completely arbitrary. It's just because of our machine has 8 cores.
I can just show one thing here. We're getting back here. Now we're seeing we've got so few ships running, we're actually only using 2 of the schedulers. The other 4 along the baseline there, the system's just not using them. And if the operating system allows it, it would have shut down cores to do that. So it won't get, well, they're being killed pretty seldom now, so it drops very slowly. But you can just see the automatic use of the schedulers.
Another question? Yes, please. So the question was if this is special to our stack, basically that we can change the behavior on the fly.
It's both. I mean, the way Lua's written, defined, and the way it's generally implemented, you can load in code while it's doing stuff. I mean, that's one of the reasons why it's being used as a script language for games, because it makes it much easier to work with the games while it's going on. So we're using that feature of Lua, and we've programmed into our system. So when we're updating the ship code, which was the set ships command I was doing before, I was actually telling each ship to update its code. So it was a mixture of both.
And it's interesting because, of course, like you maybe use from Unity 3D, it can make a lot of sense to not have to stop the system and then start it again to try something new, but you can basically experiment while it's all running. So I thought that makes sense to mention.
Yeah.
You had a question? Follow up. We did.
Yes, we did. Actually, where it hangs, the toothpaste, it's the display that hangs it. Okay, the game logic itself is relatively simple. There's no problem, but it overloads the display, and that's partially because we're very simplistic on how we do it.
Yeah.
We did a 10,000 though.
A question on this side that I'm not seeing.
Oh, I think no more questions. Yeah, other one.
So, like, if you try successful 10,000, I mean, like, what do you think is the limit? Let's say on your like 8-core machine, and like, what will be the bottleneck? Why will they?
I think I did test with. I think the bottleneck's the display.
Okay, but I mean, other than display, I mean, like, what around?
The suboptimal implementation of the sectors.
That's probably not. It could be better.
There are definitely ways that even like it's implemented now, it could still be improved using faster means of data structures. So we haven't really optimized it or run it up against how much is possible. What is sure is that just from the side of what Erlang can do in like any context, even 100,000 is not much.
From the Erlang process point of view, it's nothing. So running tens of thousands of Erlang processes is trivial. Hundreds of thousands is starting to get interesting. Millions, that's where it really gets interesting.
Yeah, it's the same. I mean, with Voltdb, I have been doing benchmarks for Node.js and for Erlang, and I have ramped it up to 2.7 million operations a second. Actually, the benchmarks I did, there were transactions that were actually combinations of reads and writes and materialized views, so that each transaction was actually 6 operations, and I ramped it up to 800,000 transactions a second. And if you use Voltdb as an interface, for example, to a web server where people can buy stuff, and so you have to try to make a live update into the game, you don't have to write 60 frames a second. I mean, you would pick an interval that makes sense, and even if you take only every 5 seconds or something, that's probably good enough, and that's not going to be a challenge.
Yeah. So, for example, in this simple test, we were at the same time we were changing the display. When we changed sectors, that's when we were writing out to Voltdb, just giving our position and some statistics or some information for each ship.
So, last question.
Nope.
No last question. Okay, then I say thank you very much. Oh, come up here.